as we're getting started, I want to draw your attention to the objectives for today. So by the time we finish this lesson of notes, the goal is for you to be able to choose and apply an appropriate coordinate system for whatever problem you're running that involves vectors, to be able to use the Pythagorean theorem and the tangent functions to calculate the magnitude and the direction of a resultant vector, and to use the sine and cosine functions to resolve vectors into their components, which are all sorts of big words that will make more sense as we move through this. Beginning, coordinate system. When we describe the motion of an object that was moving in a straight line, we placed it along one axis. So in the example that the book gave of the little salamander climbing up and down the tree, they put the salamander on the y-axis. Okay? So that's easy to do when you only have one direction of motion. But this chapter, we're digging into two-dimensional motion, and that comes with two different ways that you can use your coordinate systems. Okay, the first way is that you can just move the x-axis to point in the direction, or the y-axis to point in the direction of your movement. So say your airplane is flying at an angle of 35 degrees northeast. You could just angle the y-coordinate, the y-axis, so that it points 35 degrees north of east. That would work. But the problem that this poses is that if your object changes directions, then your coordinate system is no longer pointing in the same direction of the motion, and so it becomes, you run into the same set of problems that you would with the second solution if there's any change of motion. Because in the second type you can do is just to fix the x and y axis to specific directions. So for example, you could just say y is always going to point north and x is always going to point east. Then your motion is never going to, if your motion is at an angle other than, straight up or straight east or west, it's never going to line up on those axes, but you will always know where those axes are pointed. You're not going to have any ambiguity or confusion about that. There isn't a right or wrong way to do this. You can do it either way, whichever way makes more sense to your brain. Just know that you need to stick with it for the whole of a problem. You can't switch up the way you're designating the axis halfway through a problem. As long as you pick your system and you stick with it, you will come out with the correct answer. You just have to be consistent. So whichever way makes more sense to your brain, choose that one and use it. Adding perpendicular vectors using trigonometry. So we've already graphically added these. Okay, we've learned how to use the triangle method and scales and protractors and rulers to come up with an answer. But because there's so many moving factors there's a lot of room for error. We can remove some of that by doing this mathematically through the use of a couple of trigonometry equations that you may or may not be familiar with. Hopefully you're familiar with them, so that will make today a lot easier for you. Okay? When you're adding two vectors together that are perpendicular to each other, so meaning they are at 90 degrees to each other, forming two sides of a right triangle, you can use Pythagorean theorem and the tangent function to calculate their magnitude and direction. So you would use Pythagorean theorem, the a squared plus b squared equals c squared, to find the magnitude, also known as, if you're doing distance, this would be the length, right? But we say magnitude because it's not always distance, so the numerical value. And then you can find the direction or the angle that it's traveling at using the tangent function. So tangent is equal to opposite side over adjacent side. Let's think of an example problem. So in our example problem, there's an archaeologist that's climbing the Great Pyramid that's in Giza, Egypt. They know the pyramid's height is 136 meters tall, and they know its width across the entirety of the bottom of the base is 2.30 times 10 to the second meters. So they want to calculate what the magnitude and the direction of their displacement will be after they have climbed from the bottom of the pyramid all the way up to the top, assuming that they run a straight line from the middle of the base up to the peak. If we were going to set this problem up, it would set up something like this. So we would have given to us the displacement on the y-axis, which is 136 meters. And we know that they gave us the entire length of the base, so we have to divide that in half if we want just the base of our right triangle here. So that's 115 meters. What we don't know is we do not know the magnitude of the displacement, which we'll represent with the letter D, and we do not know the angle of their displacement, which we will represent with the Greek letter theta. Okay. So, back up. What should our equations look like? So we're going to wind up with equations of the displacement squared is going to equal delta y squared plus delta x squared. And then for the angle, we have to get the angle by itself. So theta is going to wind up equaling the inverse of tangent times our delta y and our delta x. Okay, so using these equations, see if you can't come up with the correct answer. Because we had to move it from one side of the equation to the other. So you would multiply by the inverse. So if you run the calculations out, you should wind up with a displacement of 178 meters. And you should wind up with a angle of 49.8 degrees. Is that roughly what we came up with? What I'd like you to do now is to flip to page 89 in your book, and there's a set of practice problems. So you can see the problem we just worked out in the book as well, and there's a set of practice problems that come after it. You're going to do number 2 on your own, and then we'll run it on the board and see how we do. So I'm going to let you set this one up, do your own drawing, do your own equations, and then we'll try it together. Let's run that one on just like a blank whiteboard here. So, the problem says that the pirate walks north first, a distance of 45 meters, and that then they turn and they walk east. Not as far this time, only 7.5 meters. Okay, so we want to find the resultant displacement, which would be this one right here. Okay, so in order to find both direction and magnitude, we need both of the equations that we just used. So we should do 45 squared plus 70 or 7.5 squared square rooted, which comes out to should come out to, I have 45.6 if we want the correct number of significant figures. Well, yeah, once again, this book is not great at remembering its significant figures. So yeah, if we're doing correct number of significant figures, we should round to 2, so we should have 46 meters. And then we have to again use the tangent inverse times so if this is the angle we're solving for, the opposite over the adjacent which should have you come out with a very small angle of 9.5 degrees east of north. That roughly what we came up with. If there are no questions, then we will move on to the next section, which is resolving vectors into their components. Vectors that are traveling at an angle can be resolved into their horizontal and vertical components. So all that means is if I have a vector that's like this, I can resolve it into a horizontal component and a vertical component. All of them should have both of those. So when we're talking about components, we're talking about the horizontal motion and the vertical motion that make up the resultant, the vector motion, okay? We can solve for them using sine. So the sine of an angle is equal to the opposite leg divided by the hypotenuse, and cosine, knowing that the cosine of an angle is equal to the adjacent leg divided by the hypotenuse. So using those two equations, we can then solve for the components of that vector. So if we're looking at an example, the example the book gives is the straight stretch of interstate highway that runs from Mettler, California to a point near Buttonwillow, California, is 53.0 kilometers long, and it makes an angle of 48.8 degrees north of west. They want to know what the western and northern components of that highway segment are. So if we set up this problem, it would look like this, where we have the hypotenuse, okay, and we have that angle that they gave us, north of west. So then it's our job to use sine and cosine to solve for the x and y components. So the equations that you will wind up using will be that you can solve for delta x by using the hypotenuse times the cosine of theta, and you can solve for delta y by using the hypotenuse times the sine of theta. It is easy when working these problems, especially when the first one you see is set up like this, to assume that cosine will always be used for the x component and sine will always be used for the y component, but it's not always set up that way. So make sure that you are actually looking at where is the angle that they gave me, what is the opposite leg, what is the adjacent leg, and make sure you're using the right function for the right displacement. Real quick before you leave, your numbers that you should have come up with should be that delta x should be 35.0 kilometers and delta y should be 39.8 kilometers.
Yes.